Hello friends, welcome to engineering tutorial. Now in my previous video I discussed about some of the basic concepts related to inductors, which is a circuit element. Previously in videos previous to that we discussed about the basic concepts related to resistors. So we completed resistors, inductors, and now today we are going to discuss about another basic circuit element, which is capacitor. Okay, so first the definition of a capacitor. What is a capacitor? So a capacitor basically is a combination of two conducting plates. Okay, two flat plates, two conducting plates which are separated by some distance by an insulator or dielectric material. So if you take two conducting plates, that is, connect them across a voltage source and separate them with an insulating medium, keep some insulating medium in between them, then you form a capacitor arrangement. Now that combination is popularly called as parallel plate capacitor. It consists of two plates, okay, flat plates, which are separated by some distance with a dielectric or insulating medium in between. Okay, so what happens is that the plate which is connected to the positive terminal of the voltage source, it acquires a positive charge plus Q, while the plate which is connected to the negative terminal of the voltage source, it acquires a negative charge minus Q. Now pay attention that the magnitude of the charge acquired by both plates is the same, Q, just their sign is different. Okay, one is positive, one is negative. The net charge acquired by the parallel plate capacitor has magnitude Q. Okay, now this is the symbol of a capacitor which you will be using in circuit theory or network theory. Now these two bars, okay, it represents the two parallel plates, conducting plates. Okay, so this is the symbol of a capacitor. Now the charge which is acquired by the parallel plate capacitor arrangement, which has a magnitude of plus Q, that charge is directly proportional to the voltage which is applied to the capacitor arrangement. The amount of charge acquired by the capacitor arrangement or the amount of charge stored by the capacitor is directly proportional to the applied voltage, this voltage. So we can say Q is directly proportional to V, where Q is the charge acquired by the capacitor and V is the applied voltage. Now, as there is a proportionality relationship here, it means there will be a constant of proportionality, and that constant of proportionality is C. Q is equal to CV, where C, capital C, is the capacitance of the parallel plate capacitor, and that capacitance value is equal to Q by V, which is the ratio between the charge stored by the capacitor arrangement and the applied voltage. So in simple terms, we can say that the capacitance is the ratio between the charge stored by the parallel plate capacitor or the charge acquired by the parallel plate capacitor divided by the voltage which is applied across the two plates. Okay, capacitance is charge by voltage, and the unit of capacitance is farad. The unit of resistance is ohm, the unit of inductance is Henry, and the unit of capacitance is farad. Capacitance is measured in terms of farad. Okay, so this is the important relationship of capacitance, which is involved in capacitance, which will be used while dealing with electrical circuits. In case of resistance, it was V equals to IR. In case of inductance, it was V is equal to L di by dt. In case of capacitance, it is this C is equal to Q by V. These are the three basic relationships which are involved in resistor, inductor and capacitor, which you should remember, which you should know. Only then you can analyze the various electrical circuits in a proper way. So this is the very important relationship. All the other relationships with respect to capacitor will be derived from this basic relationship. C is equal to Q by V. Capacitance is equal to charge by applied voltage. Okay. So next we are going to study about the voltage which is developed across the capacitor arrangement and the current flow through the capacitor. Now here we will discuss some concepts related to the capacitor voltage and current. So in both of these expressions, in capacitor voltage and current, this expression Q is equal to CV will play the role of the initiator. We will derive those expressions from this basic expression. Okay, so this is very important in reference to capacitor. So we just studied that the capacitor is the ratio between the charge stored and the applied voltage, that is C is equal to Q by V or Q is equal to CV, where Q is the charge stored. Now we know that the current is actually the rate of flow of charge with respect to time, or the time rate of flow of charge, which is nothing but the derivative of charge with respect to time, dq by dt. I is equal to dq by dt. So if we put this value of Q, CV here in this expression, we will get the capacitor current, or the current flow through the capacitor, is equal to the derivative of CV. Now out of this, the capacitor or the capacitance is a constant value, so it will go outside. So I is equal to C dV by dt. Actually, the current flow through the capacitor and the voltage across the capacitor, they are time varying entities. Okay. So the current flow through the capacitor is given by this expression, I is equal to C dV by dt, where I is the capacitor current and V is the voltage which is applied across the capacitor. Or in more general terms, we can write it as I subscript C is equal to C into dVc by dt, where I subscript C is the capacitor current and V subscript C is the capacitor voltage. So this is the expression of capacitor current. IC is equal to C dVc by dt, where IC is the capacitor current. Next, we have to determine the expression for capacitor voltage. Now, we write the same expression which we just derived, IC is equal to C dVc by dt. So, dVc is equal to 1 by C into IC dt. If we integrate both sides and the limit is kept from minus phi to t. So, if we integrate both sides, we will get Vc, or the capacitor voltage, is equal to 1 by C with IC integrated from limits minus phi to t dt. Vc is equal to 1 by C minus phi to t IC dt. Now, if you remember, in case of inductor, okay, in case of inductor, the inductor current IL was given by 1 by L integration of VL from minus phi to d dt. That is, IL is equal to 1 by L minus phi to t VL dt. We did that in case of inductor current. Now, in case of inductors and capacitors, they are different from resistors in a way that they are energy storing elements. Inductors and capacitors are energy storing elements. Inductors store energy in magnetic field and capacitors store energy in electrostatic field. So whenever they are connected in a circuit, the voltage across the capacitor and the current flow through the inductor, they cannot change instantaneously. In case of resistor, the voltage drop across the resistor will reduce from the maximum voltage to 0 as soon as the current flow through the resistor is 0. But in case of inductors and capacitors, it will not be like that. The voltage across the capacitor will not abruptly change from the stored value to 0 instantaneously. It will not change like that. It will take some time to discharge. Okay, it will take some time to discharge and lower its voltage value. Similarly, the current flow through the inductor cannot change instantaneously. It means that if we switch a circuit, okay, if we switch a circuit involving inductors with some initial value of inductor current, if we switch off the circuit, the current flow through the inductor will not be 0 immediately. It will take some time in terms of milliseconds or microseconds, and that depends on the time constant. But that is something related to transient analysis. That concept is related to transient analysis. We will study that in transient analysis part. That is a different area of circuit theory. But just why I am including this minus phi to t. Now the interval from minus phi to 0 is the past state of the capacitor voltage, or the past state of the capacitor. Okay, the previous voltage value which it stores itself, and from 0 to t is the current time. Okay, from 0 to t. So we include minus phi to t because of its energy storage property, and we also do the same in case of inductor currents because of the energy storage property of inductors. Okay, so the simple thing here is that capacitors and inductors, they store energy. They are capable of storing energy for a certain period of time. Capacitors store energy in the electrostatic field and inductors store energy in the electromagnetic field. But resistors do not possess any such property. They do not have energy storage property. So that's why we derived these two expressions of capacitor voltage and current. Okay, here IC is equal to C dVc by dt and Vc is equal to 1 by C minus phi to t IC dt. So these are the two important expressions related to capacitor. One is for capacitor current, one is for capacitor voltage. So next we are going to discuss about the sign convention. Okay, sign convention means the polarity of the voltage across the capacitor. Now this is very important because most of the time mistakes happen while determining or while assigning the polarity of the capacitor voltage. We discussed sign convention part while analyzing the voltage drop across a resistor. We also discussed that while evaluating the voltage drop or the voltage across inductor, and we will do the same while analyzing the capacitor voltage. So here in the first case you can see we have a parallel plate capacitor or a normal capacitor with capacitor current flowing from left to right in this direction. Now pay attention to the polarity which is placed on the capacitor. It is plus and minus. It is flowing from positive sign to negative sign internally through the capacitor. Here the polarity of the voltage across the capacitor is also measured in the same direction, in the same way. Here also positive, here also positive, here is negative, here is negative. Okay, the voltage across the capacitor is measured in the same direction of the polarity which is assigned with reference to the current flow. Now current is flowing from positive to negative terminal of the capacitor internally. It means that this capacitor is absorbing power from an external voltage source or power source. So that's why the positive to negative sign is placed. The voltage across the capacitor is measured in the same direction. So here it is positive, here it is positive, here it is negative, here it is negative. That's why the voltage across the capacitor will be 1 by C minus phi to t IC dt, or plus 1 by C minus phi to t IC dt. It is also same as that. In this case, the current flows through the capacitor in the same direction, from positive to negative internally through the capacitor. We cannot change that. It is always constant because the capacitor is absorbing power. But here, the voltage is measured in the opposite direction, from positive to negative, from right to left. It is opposite to the direction of the polarity which is placed on the capacitor with reference to the current flow through the capacitor. Current is flowing from positive terminal to negative terminal internally, but the voltage is measured in the opposite direction, okay, from here to here, from positive to negative, from right to left. So here it is plus, but here it is minus, here it is minus, here it is plus. So in this case, the voltage across the capacitor will be minus 1 by C minus phi to t IC dt. The magnitude of both the capacitor voltages are the same, but here it is plus 1 by C minus phi to t IC dt, and here it is minus 1 by C minus phi to t IC dt, because the voltage across the capacitor is measured in the opposite direction to that of the polarity of the current flow in the capacitor, in reference to the current flow in the capacitor. Always remember, current always flows from positive to negative terminal in any circuit element, be it a resistor, be it an inductor or a capacitor, because they always absorb power. Okay? So this is about the sign convention, which is very important. Now, another possible interpretation of the parallel plate capacitor, that is the expression of capacitance, can be taken in this way. Okay, we know that Q is equal to CV, or C is equal to Q by V, which is the ratio between the charge stored and the applied voltage. That is the expression of capacitance of a capacitor. Now that expression is used in circuit theory or network theory while analyzing electrical circuits. But in instrumentation, in industrial instrumentation for manufacturing of sensors and transducers utilizing the principle of capacitance, there is another possible expression of capacitance of the parallel plate capacitor, that is given by C is equal to epsilon A by T. Now, we know that in a capacitor or a parallel plate capacitor, which we have two conducting plates which are separated by a certain distance. Now let the distance of separation between the two plates be d. Now both the two plates are kept one above the other, and they can move laterally. They can move laterally or sideways. As a result of that, as a result of the sideways movement of the parallel plate capacitors, that means the first plate can move either to the left or to the right, and the second plate can also move to the left or to the right, or it can happen like one of the plate is fixed and only one plate is movable. It can also happen like that, and there is also to and fro movement of the two plates, that is the plate can move either forward or backward depending on the type of sensor or transducer we wish to fabricate. So this results in a change in the distance between the two plates or a change in the area of overlap between the two plates. Now area of overlap is actually the portion of the two plates or the area of the two plates which lie one above the other. This portion and this portion which does not lie one above the other are not in use. Only the portion, this much area and this much area which lies above one above the other contribute to capacitance. The distance of separation between the two plates and the area of overlap between the two plates, which the portion or the area which lies one above the other. So that is given by C is equal to epsilon A by D, where A is the area of overlap of the two plates, the portion or the area which lies one above the other, and D is the distance of separation between the two plates. Epsilon is the permittivity of the medium. Now, the permittivity is a property of a material to pass or to influence an electric field which is applied across it. Now, we know that both the parallel plates are separated by a dielectric medium or an insulating medium. So, permittivity of the dielectric or insulating medium is the ability of that dielectric material to pass an electric field through it. How much of the electric field is passed by the dielectric medium? That is given by the permittivity. For now, that is a thing which we will deal with when we go to the instrumentation and industrial instrumentation part for fabrication of sensors and transducers. But just for now, you understand that the capacitance can also be expressed as epsilon A by D, where the capacitance is directly proportional to the permittivity of the medium, which means more the permittivity, more the capacitance. It is directly proportional to the overlapping area, which means more the overlapping area, more the capacitance. If the two plates completely lie one above the other, then the capacitance will be maximum, and the capacitance is inversely proportional to the distance of separation between the two plates, which means more the distance, less the capacitance, less the distance, more the capacitance. Okay? So, this is another possible interpretation or expression of capacitance of a parallel plate capacitor in addition to C is equal to Q by V, that expression. This expression is used in industrial instrumentation for fabrication of sensors and transducers based on capacitor principle. The expression C is equal to Q by V is used in circuit theory for electrical circuits analysis, and mostly we will be dealing with that expression, that is C is equal to Q by V. But just for you should know the various expression for your understanding, I also introduced this part. Okay, so here we have discussed some of the basic concepts related to capacitors. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics, instrumentation and communication engineering. Have a great day. Thank you very much.